Good afternoon, class. In today's video, what I wanted to do was to go over one term that I needed to go over before I get into the general form of relativistic energy. And that term is going to be E equals P times C, where P is the momentum of an object. Now, you might think, okay, well, that's fine, but isn't P equal to mv? Not necessarily. And the thing is, not all objects in the universe have to have mass in order to have momentum. Now, of course, you might be thinking, why is this? How can this be? And so what I did was I drew out a little diagram for you to give you an example of how that could be possible for something, especially light, which we all know has no mass, to be able to influence something far away and still, in other words, transfer energy across vast distances without having any mass to speak of. So in this case, what I did was I took an ocean wave. So if you think about an ocean wave, there's a lot of energy being transferred, right? The wind blows on the water and then it forms waves. Great, we've got energy being transferred. It feels like the water is moving, but is the water moving? If you look at any bit of this ocean, sure, some of it moves a little bit, but so some of this will move towards shore, but it'll get moved back pretty much right away. So essentially, you've got almost no motion of the actual water itself. Little bits, obviously, but not much motion of the water at all relative to the overall ocean. So there's no mass transfer, but there is a huge amount of energy being transferred to the beach over here. So in this case, so that's why one of the ways you can think about it is that if you talk about a wave, something that's purely a wave, like light, because light is both a wave and a particle in terms of the photon and the wavelength that it carries, you can have energy being transferred through something without any mass being transferred. So you don't have to have mass in order to be able to transfer energy, but because you're now transferring energy along, somewhere, whether it's through the vacuum of space or, through water like this, what's happening is that this actually does describe what momentum is, because momentum is a directional property where something can influence something else after, once there's an interaction between them. So essentially, if you've got a photon, it could interact with something else, maybe another photon, maybe maybe a particle of water, like on the ocean like this, and there will be an interaction, and even though light has no mass, so therefore you think maybe there's no momentum, there is momentum because the light is traveling in a direction, so it's got a directional property, and there is an ability for light to influence something else because it's carrying energy with it. So that means that light, therefore, must have momentum. So I wanted that to be clear, wanted that to make sure that I had that at least conceptually in our heads, because in the next video, what I'm going to do is I'm going to pull out the actual general result for energy, in relativistic terms, and so this will, this will be assumed to be understood as light having momentum. So that concludes this video. Good luck in your studies. May the force be with you.